Analysis of deep learning models for diabetic foot ulcer detection using thermal foot images. So I'm Dhanashri Londhe. I'm research scholar, second year of PhD from pursued in GS Raisoni International Skill Tech University, Yerwada, Pune. So my topic is about analysis of deep learning models for diabetic foot ulcer detection using thermal foot images. So the abstract for this is that in this system, we are going to study about different deep learning models which are going to give you comparative study of thermal images of plantar foot for detecting diabetic foot ulcer at early stages. So models that we are going to use here are mobile net V2, efficient net B0, ResNet 50, DenseNet 121, and they are evaluated against accuracy level, sensitivity level, specificity, and AUC. So in this system that we have developed, in this ResNet 50 has performed best, both with high precision as well with high sensitivity and AUC. So the introduction of this is that diabetes mellitus is the major global health problem, and diabetic foot ulcer detection is serious complication that can lead to infection and amputation if it is not detected in earlier stages. So the traditional screening method is very time consuming and it is subjective. So here in this case, infrared thermal images are provided, which provides non-invasive and contactless way to detect temperature changes linked to early detection of the ulcer formation. Ulcer formation. Okay, so recent advances in deep learning and CNN models enables automatic analysis of deep learning images with high accuracy. This study uses transfer learning models such as mobile net V2, efficient net B0, ResNet 50, and DenseNet 121 to identify the best approaches for DFU detection from plantar thermal images. The goal is to develop a cost-effective, scalable early screening solution for the diabetic foot. Yeah. The problem statement is that the traditional methods are using um, early detection of DFU, that is diabetic foot ulcer, are very challenging, and existing systems are often subjective and not suitable for large scale screening. So there is need of the automated system that analyzes and compares different deep learning models to accurate detection of the DFU, diabetic foot ulcer, from the thermal images. The methodology that we have used here is first phase of methodology is thermal image pre-processing. So here we need to pre-process the thermal images. So they are resized to get uniform resolution and compatibility with the CNN models for and efficient batch processing. Next, we need to perform pixel intensity normalization. So consistent temperature value ranges and improves model training stability. Noise reduction technique. So remove the sensor noise and environmental variation while preserving important thermal patterns we need to perform. Contrast enhancement was performed to highlight small temperature differences associated with the early inflammation. Then we have to select region of interest. It focuses on the plantar area such as heel, then metatarsal heads, forefoot, where ulcer commonly develop in the diabetic patient. Then we need to improve image quality. For improvement of the image quality and feature extraction, we need to perform pre-processing of the images. After that, we will apply deep learning models. So the deep learning models are, we are going to use CNN architectures as mobile net V2, efficient net B0, ResNet 50, and DenseNet 121 for classification of plantar thermal images. The model selected due to They had high accuracy, efficiency, and stability for medical image analysis. Transport learning was applied by using pre-trained weights and replacing the final layer for binary classification, ulcer and non-ulcer. Models were fine-tuned on thermal images to learn patterns related to inflammation and abnormal temperature distribution. Comparative analysis was performed to evaluate performance, computation efficiency, and stability for real-world diabetic foot ulcer detection uh, screening system. Next is training strategy. Training strategy, we are here using cross entropy loss and Adam optimizer for stable and efficient learning. Now here, cross entropy helps for improving the prediction accuracy by minimizing difference between predicted and actual class. Adam optimizer enables fast coverage and adaptive learning for making it effective for medical image classification. Next, we are using here the data augmentation for reducing the overfitting and improve the model performance. Augmentation performs rotation, horizontal, vertical, flipping, and scaling of the images. This techniques increases dataset diversity and helps the models to learn robust generalizable features. These training strategies ensure accurate, stable, and reliable DFU diabetic foot ulcer detection model suitable for clinical applications. The results and performance metrics we are using to evaluate performance are accuracy, precision, recall, the F1 score, and AUC. Accuracy is measures the overall percentage of correctly classified images. Precision indicates how accurately the model identifies ulcer cases while reducing false positive. Sensitivity or recall measures the model's ability to correctly detect actual ulcer cases and minimize missed diagnosis. F1 score provides balanced evaluation of combining precision and recall, especially useful for imbalanced dataset. AUC, area under ROC curve, evaluates the model's ability to distinguish between ulcer, non-ulcer image across different thresholds. These metrics provide comprehensive and clinically relevant evaluation of diabetic foot ulcer detection models. This is the quantitative result of different models against accuracy, precision, recall, F1 score, and AUC. So this is the diagrammatic representation of the comparison, AUC comparison, and the accuracy comparison I have shown. Then discussion is that the experimental result shows deep learning models can effectively detect diabetic foot ulcers from plantar thermal images, enabling contact, non-contact, and automated screening. Thermal images helps to identify subtle temperature variations and tissue damages and the inflammations. Then, among all the models, ResNet 50 achieved best performance, providing strong balance between sensitivity and specificity. High sensitivity ensures most ulcer cases are detected, while high specificity reduces false alarms. MobileNet V2, although lightweight and computationally efficient, showed comparatively lower recall, indicating some ulcer cases may be missed. These results highlight the model selection should depend on the application. High accuracy models like ResNet 50 for clinical environments, lightweight models for large scales and remote scaling. Overall, the study demonstrates that deep learning with the thermal imaging is the promising approach for early and automated diabetic foot ulcer detection in real-world healthcare settings. The conclusion is that the deep learning based DFU detection framework using plantar thermal images for early, accurate, and non-invasive diagnosis. The thermal images captures temperature variation related to inflammation, infection, and tissue damage without physical contact. The system uses transfer learning with CNN models to learn uh, diabetic foot ulcer patterns from limited medical data set. Comparative analysis of multiple models showed ResNet 50 achieved best balance of sensitivity and specificity for reliable screening. The framework is scalable, cost effective, and suitable for clinical use, remote monitoring, and telemedicine. So, this is about my presentation. Thank you for your time and your cooperation.